Hello, everyone. This talk is about identity-based encryption from LWE with more compact master public key. I am Farhad Abla. IBE is a generalization of public key encryption. After generating the public key and the master secret key, the master public key is publicly sent to the users. And any user can encrypt the message under the MPK and the identity of the target user. After receiving the ciphertext, a target user will use its own secret key to decrypt it, and only can decrypt the underlying ciphertext, which is encrypted under its identity. The concept of IBE is introduced by Shamir, and the first construction is given by Bonnet and Franklin. A common security notion for IBE is adaptive security, where a challenger first generates the MPK and MSK and sends the MPK to the adversary. The adversary can query many polynomially bounded identity key queries. After that, the adversary sends a challenge identity and two messages to the challenger. The challenger randomly selects one of the messages and encrypt the corresponding message under the challenge identity and generates the ciphertext and send it back to the adversary. Then the adversary guesses which message is encrypted. The selective security is similar to the adaptive security, except that the challenge identity is decided by the adversary at the outset of the game, before giving the MPK. There are many constructions based on the number theoretic assumptions. Among them, the Waters design is more compact, where Waters gives an adaptively secure IBE, which is as compact as selective IBE. But the construction is based on the number theoretic assumptions, which is not secure in the quantum environment. So there's a question that can we construct a post-quantum adaptive IBE as compact as selective IBE? Motivated by this problem, there's many remarkable works. Among them, based on the LW constructions, ABB1 constructed a adaptively secure IBE, which that scheme needs ON matrices in the MPK. More recently, the Yamada 17 gives an IBE scheme based on the LW, where the MPK needs O log N matrices. But the scheme needs Barrington's theorem, and thus modulus of the scheme is cannot be given, and so we say this scheme is implicitly designed. So there's a natural question is that can we construct a lattice-based IBE with more compact MPK without Barrington's theorem and explicitly designed? From Yamada 17, there is no significant improvement for this work, but in our work we give a more compact IBE scheme over LW problems. Our construction is explicit, and the master public key of our IBE scheme contains omega log n, omega log n over log n matrices. To construct a more compact IBE, we design a more compact LW-based homomorphic equality test algorithm, which can test for integrals compactly test for integrals in 0 to log n over log n. Note that the previous LW-based IBE scheme needs omega log n, so our IBE scheme is significantly better than the state-of-the-art works, and which is implicitly designed, and which our design is explicit. previous LW-based compact homomorphic equality test algorithms only works for Boolean numbers, and ours can work 0 to log n over log n. Let's recap the constructions of ABE before giving our constructions. In the IB scheme of the ABB10, there are L plus 1 matrices, and which consists of the MPK, and MSK is the trapdoor of the matrices. A lattice generated by the matrix A, and the TA is the corresponding trapdoor. The to generate a secret key for an identity ID, first compute the a matrix FID. Since we have a trapdoor of A, so we can generate Gaussian sample of these matrices. We can generate that this is a Gaussian sample which satisfies FID times SKID equals to U. This can be sampled by sample left algorithm using the trapdoor of TA. In the simulation game, to simulate a secret key for an identity without giving the MSK, we don't have the trapdoor TA in the simulation game. So the ABB10 observes that if the FID is the homomorphic evaluation of so-called admissible hash function, if the hash value of this function is for the query identity is equals to 1, then the corresponding this matrix is a G trapdoor of FID. So using the sample right algorithm, the simulator can generate a corresponding secret key. For the challenge identity, this hash value is equals to 0, and the simulator can generate a corresponding ciphertext. We know that this hash to homomorphically evaluate this hash value, we need a L matrices. So we need a B1 to BL matrices in the MPK. To improve this compactness, the construction of AFWW21 constructed a ring LW based IBE, which needs omega 1 ring matrices in the MPK. First, they construct a basic hash function, which on input and ID, the hash function outputs ECC or ID, and this is a matrix. This is a vector ECC error correcting code of an ID, and selects the alpha as place and minus beta. They know that this simple hash function is not satisfies the partitioning property, so they parallelly repeated this basic function and generates a repeated hash function, and then embedded this repeated hash function into a ring element, and they observe that this this hash function, the final hash function, is can have a partition property, and which is a admissible hash function for IP. Inspired this construction, we follow the first two steps. Given the ID, we map the ID to a ECC ID and select the alpha as place and minus beta, and we repeat this basic hash function for t times. T is about omega 1 as the previous construction of AFWW21. Then we embed this construction to a number. This is different from the AFWW21. We observe that this is admissible hash function and can be used to construct a IBE. So the problem is that can we more compactly homomorphically evaluate this admissible hash function. To homomorphically evaluate this hash function, we rewrite this hash function as follows. And if j is equals to alpha I, then ECCD ID, the j is alpha, and which is equals to example 1. If j not equals to alpha I, then this term equals to 0, and the multiplication is 0. So this function is equals to double function. Note that if we're given the homomorphic evaluation of this one, and given the homomorphic encoding of beta I, then we can homomorphically evaluate the whole admissible hash function of this one. So this problem is, can we construct, more compactly construct a homomorphic equality test of j and alpha I, where alpha I is from 1 to L. So our goal is to homomorphically construct, homomorphically evaluate the equality test. The previous approach is as follows. Given the encoding to homomorphically evaluate alpha if alpha equals to j, the previous approach encoding h bits of alpha and bitwise compared with the j. And where ji is ith bit of j and alpha I is ith bit of alpha. It's not hard to find that this kind of homomorphic equality testing needs log L matrices to encode alpha for one matrix for each bit of alpha, and which is somewhat non-compact. To construct a more compact one, we observe that from the Lagrange interpolation, pj alpha, this polynomial or this evaluation is equals to 1 if j equals to alpha and j not equals to alpha, then the evaluation equals to 0. We use a Lagrange interpolation, which is exactly a equality testing. We observe that if L equals to ON, then the homomorphic evaluation of a polynomial pj alpha results in exponential modulus, which is not desired for the IBE, and we don't want that. This evaluation results in a exponential modulus for if L equals to ON, and which is desired for ECC as the AFWW21. However, for if L equals to log n over log n, then the homomorphic evaluation of the above function, this function Pij, leads to a small polynomial modulus, and a compact homomorphic evaluation for the range 0 to log n over log n. So if L is more smaller, then we can use the above Lagrange interpolation. So from this observation, for larger ranges, we just represent the alpha into L-adic representation, and we can have more compact equality test for alpha. That's a homomorphic equality testing for alpha in 0 to n needs O log n over log n matrices, which is significantly better than the bitwise comparison. The bitwise comparison needs log n matrices. Therefore, applying the above homomorphic equality testing, the underlying IBE scheme scheme needs omega log n over log n matrices in the MPK. So comparing with the previous state-of-the-art constructions, our IBE scheme have significantly smaller matrices, less matrices in the MPK, which is more better than the Yamada 17. And our construction is lattice-based and explicitly designed, so we can give all the parameters explicitly. And thank you. Any questions? You can find me at my email.
Hello everyone, I'm Huiwen Jia from Guangzhou University. It's a pleasure to present on the topic of towards compact identity-based encryption on ideal lattices. This is a joint work with professors Yupu Hu, Chunming Tang, and Lin Wang. We developed an improved pre-image sampler that offers trade-offs between security and compactness. In more detail, this sampler uses a modified gadget that combines the different gadgets in MP and YGW. Besides, we incorporate the non-spherical Gaussian technique to further improve efficiency. As an application, we specify a compact identity-based encryption and present concrete parameters. The proof of concept implementation demonstrates its practicality. Let me start by some background. IBE was proposed by Shamir 40 years ago. Each user's unique identity serves as the public key. This means with master public key, one can encrypt messages directly to user's identity. The Key Generation Center was able to extract users' secret keys using the master secret key. In this way, it avoids the need for complex certificate management and has a wide range of applications in resource-constrained environments. In contrast, in the traditional PKI-based public key encryption, each user has to set up his public key certificate by the certificate authority and verify the validity of other users' certificates before use. The first IBE schemes were built on bilinear map and quadratic residue assumptions, and have been improved by subsequent works on security, efficiency, functionality, etc. To resist the threat of quantum computers, various post-quantum IBE schemes have been proposed under different assumptions. Just as the basic encryption and signatures, among these constructions, the lattice-based IBE has the best performance. However, in lattice-based IBE, both under the standard model and the random oracle model, the key extraction procedure heavily relies on the pre-image sampling algorithm. This hinders the practicality due to its low efficiency. Besides, the pre-image sampling algorithm is crucial for many advanced schemes as well. Therefore, it's important to improve the efficiency of this algorithm for the practical use of lattice-based cryptography. So, what is pre-image sampling? Actually, it's a lattice trapdoor inversion algorithm for the attached one-way function. The function is indexed by a short and fat matrix A defined over the Q and maps the input X with bounded norm to AX. The hardness of the small integer solution problem ensures the difficulty of inverting F. Specifically, inverting F can be phrased as solving the closest vector problem on the orthogonal lattice defined by matrix A. But magically, with a trapdoor, one can efficiently produce a short preimage. In early proposals, the trapdoor is a short basis, and the trapdoor inversion is implemented by deterministic Babay's CVP algorithms. However, the preimage generated in this way leaks some information about the trapdoor, and it has been broken by statistical attacks. The provably secure lattice trapdoor inversion was initiated by GPV in 2008. It can be viewed as a randomized version of the Babay's nearest plan algorithm, and the distribution of the output preimages is independent of the trapdoor. According to the underlying algebraic structure, the GPV trapdoor inversion framework can be instantiated on n-true or hard random lattice. Generally, the n-true based has good performance, but its implementation is complex and has only limited use cases. In contrast, the gadget-based is versatile, compatible with LWE, and easy to implement, but it suffers from large sizes. This work aims to efficiently instantiate the gadget-based GPV IBE. In GPV IBE, the short and fat matrix A serves as the master public key, and the key generation center extracts users' secret keys using the corresponding trapdoor as the master secret key. Then the dual regular encryption is used to protect the message mule. To decrypt correctly, the inner product of the secret key X and the noise vector E used in the encryption should be less than a quarter of the modulus Q with overwhelming probability. Currently, there are untrue-based instantiations and subsequent optimizations. The absence of efficient specification of GPV-IBE on hard random lattice motivates us to study the corresponding pre-image sampler. The first gadget-based pre-image sampler was proposed by Misancio and Packard, where the trapdoor T is no longer a short basis and satisfies AT equals G. Here G is the gadget matrix and is defined as the tensor product of the identity matrix and the gadget vector G, which has a special structure. In this way, inverting F indexed by A is reduced to inverting F indexed by G, which is simple and fast due to its well-structured basis. At a high level, the MP sampler consists of two main parts. In the offline phase, it samples a perturbation vector from the Gaussian distribution with a specific covariance. Then, in the online phase, it samples a short Gaussian vector from a specific coset. Finally, pre-image is output by a simple linear transformation. Although the MP sampler is optimal in speed after various optimizations, it still suffers from large sizes due to the wide gadget. The CGM put forward the notion of the approximate trapdoor and replaced the MP gadget vector G with a truncated version F, resulting in a size reduction of about one-half. Recently, YGW used a square matrix as the gadget to minimize the sizes. Specifically, their gadget can be instantiated by the identity matrix, scaled by the parameter P. This means the gadget vector has only one dimension and is simply the scalar P. Then, in the online phase, the semi-random gadget sampler first computes a small error E deterministically, such that V minus E equals PC. Then it samples a short Z from the coset of a one-dimensional lattice, determined by Q and C. In comparison, YGW is the most compact sampler, and the Eagle signature scheme based on YGW is the most compact construction in the hash and sum paradigm on hard random lattice. Here we note that as the simplest application, the hash and sum signature only requires the pre-image norm to be roughly equals the modulus Q. However, other applications, including the GPV-IBE, usually requires the pre-image norm to be much less than Q. Although increasing the lowercase parameter Q in YGW may support the GPV-IBE, we think it's inconvenient for other applications due to the introduced relatively large errors in the pre-images. Based on the previous works, we propose a new sampler that provides trade-offs between security and sizes, thus offering more flexibility in parameter selection. In the online phase, we combine the MP gadget with the YGW semi-random technique. In more detail, we first expand the gadget vector from a scalar in YGW to a vector. Then, given any target V, we compute an error E deterministically such that V minus E equals PC, just as in YGW. Finally, we sample a short Z from the coset of a W-dimensional lattice, determined by G and C, as in the MP. In the offline phase, we adapt the non-spherical Gaussian technique to further reduce the pre-image norm. To be useful, it's particularly important to show the simulatability of our sampler. which means the simulator can generate a specific joint distribution without the trapdoor. This enables the simulator to answer the secret key queries in the security proof. The lemma states this property for the gadget sampling. Its proof is a direct generalization of that in YJW. Based on this lemma and the Gauss linear transformation lemma, we can show the simulatability of our sampler in the theorem. That is, we require the following two distributions be indistinguishable. In the first distribution, a uniformly random target U is sampled. Then, an approximate preimage X and an error E are generated by our sampler. In contrast, in the second distribution, the approximate preimage X and the error E are sampled from suitable distributions. Then the target U is computed. We omit the details of the proof. The table comparison clearly shows that our gadget sampling is a combination of MP and YJW. Note that for the modulus Q of the same size, the norms of gadget preimage Z and error term E are smaller than those in YJW, because B is much smaller than Q and the parameter P is much smaller in our sampler than in YJW. But the gadget dimension is increased. Therefore, we reduce the preimage norm at the cost of enlarging sizes. Finally, note that our sampler is equivalent to YJW when W is 1. This means our sampler is a natural generalization of YJW. As an application, we instantiate the GPV-IBE on the commonly used power of 2 cyclotomic rings. In the setup, we sample a uniformly random A and a square matrix R from suitable distribution. This means the dimension of the gadget vector is 2. Then, the rest of the master public key is computed as shown in the dotted box. Clearly, this gives the ring LW instances. To facilitate the key extraction procedure, we compute an upper triangular matrix C as part of the master secret key, which is the Cholesky decomposition of a symmetric matrix defined in the dotted box. To extract the user's secret keys, the key generation center with the master secret key simply runs the preimage sampling algorithm with the hashed ID as the target. In more detail, it performs the offline sample P and online sample G respectively. After that, it performs a linear transformation and outputs the secret key. Note that the norms of the upper and lower parts of the perturbation vector produced by sample P are different, due to the use of the non-spherical Gauss technique. Actually, in our proof of concept implementation, we use the GM algorithm to accomplish the sample P, which samples the perturbation vector by gradually updating the center and the covariance matrix using the Schur complement at the ring level. To do so, we require many subroutines. For instance, sample the continuous Gaussians, sample the discrete Gaussians over the integer, perform the polynomial multiplication using the fast Fourier transformation, use the RNNS encoding technique to compress the preimages, etc. Then the dual Ragal encryption is used to head the message. To use a slightly smaller modulus Q, we also use an error correcting code to ensure correctness. Our GPV-IBE is named by the semi-random non-spherical Gaussian, and we present two concrete parameter sets. A comparison with MSO shows that the Entropy-based GPV-IBE is more compact than ours, although we offer slightly higher security. This is an inherent gap, as the underlying sys problem instance has higher dimensions. However, it's worthy to note that our instantiation removes the intro assumption, thus avoiding the complex intro chapter generation. This is an attractive feature, especially for applications with overstretched parameters. Besides, both the online and offline phases have room for improvement in terms of implementation. In addition, it's convenient to adapt to the unstructured setting, thanks to the absence of costly matrix inversions in the key generation. To sum up, our new sampler uses a gadget that combines the MP and the YGW, which brings more flexibility in parameter selection. We instantiate an efficient gadget-based GPV IBE. Notice that as our sampler is a natural generalization of YGW, the potential improvements on YGW applies to ours as well. And due to the use of gadget, we believe that our technique will support even more advanced instantiations. Thanks for listening. I appreciate your time. If you have any question, please feel free to contact me.